So our discussion so far helps us understand if you start from a continuous time signal, what are the frequencies in discrete time signal, or if you start from a discrete time signal, what will be the frequencies in your continuous time signal if you use ideal sampling or ideal reconstruction. Now, in the real world, we also often want to manipulate continuous time frequencies of continuous time systems. So you record a signal. We talked about, for example, stock market. You record your signal. You want to run various sorts of analysis on that to figure out whether you want to buy or sell or whatever. Although stock market signals, you often can just think of them as discrete time. You record music. Well, you are really interested in taking your music and changing its various frequencies. So all those discussions are given in terms of continuous time properties. I want to reduce 10 kilohertz frequency. I want to amplify 20 kilohertz frequency or things like that. Now, in reality, what you want is to manipulate frequencies. You want continuous time LTI systems. So you have a signal GA of t. Someone says, I want you to get rid of frequencies between, let's say, 10 kilohertz and 15 kilohertz. So you pass it through a continuous time filter with frequency response Aj omega. You get back G tilde of t. But in today's world, you want to actually, instead of really implementing this continuous time system, we want to mimic it using a DSP system. Okay, so what does it mean? You have an input signal GA of t. Now, first of all, if you are going to use the DSP system, then one of the blocks that you should often think about is the anti-aliasing filter. So let's say you have an anti-aliasing filter. It may or may not be optional. After that, you get this anti-alias version of your continuous time signal, and then you pass it through a continuous to discrete converter with time period t. And since you want to now do some operation on it, but your signal is now discrete time, you do your operation by inserting a discrete time LTI system in there. So you insert a filter, a discrete time filter, which has some frequency response h of e to the j omega to get y of n. Then you pass that y of n to a discrete to continuous converter with time period t or some other time period, and you finally get g tilde of t. Now, using a DSP system to mimic a continuous time system means that you want this entire block, which is really not a which is not really a continuous time LTI system, you want this block to have the same effect on frequencies as the block if you had a continuous time system in there. You want this combination of all these blocks to have an effective frequency response, which is what you were interested in. So the effects of anti-aliasing filter, the effects of continuous to discrete conversion, your discrete time LTI system, your discrete to continuous conversion, all of that should be captured by this frequency response so that your output frequencies are given by your input frequencies times this frequency response. If your input-output relation can be written like this, where this may be a function of many things. This will be a function of your t and other factors. If your input-output relationship can be written like this, then you know that your DSP system is acting as a continuous time LTI system. So if this relationship holds, then our DSP system effectively behaves as a continuous time LTI system. Okay? Because we know that continuous time LTI systems in frequency domain, their effect on input frequencies is multiplication with some Fourier transform. So how do we make our DSP system behave like an effective continuous time LTI system is what we are really interested in. Okay, so the design steps, if you want to do this, are the first step is someone comes to you and says that I am interested in a system that acts in a certain fashion, and that fashion of that system, the system is described through the impulse response or the Fourier transform. So someone first comes and specifies the desired continuous time system. So it could be specified through the Fourier domain frequency response or the time domain impulse response. If you are working in some field, this is all you will be told. Here is the input signal. I want you to low pass filter it with a cutoff of 10 kilohertz. So the specification will be in continuous time. Okay. That's the first thing you need, and the goal is design a DSP system such that this effective frequency response of your DSP system, which is captured through all these blocks collectively, the frequency response of that effective system is equal to what you wanted. Now, in order to do that, we have to specify the first thing we'll have to do is what is T? that we need. And that will be a function of your input signal, what's its bandwidth and all that. The second thing you will need is what should be the discrete time filter. So in this block diagram, this thing, how do you specify that? And that you can specify again either through its frequency domain expression, the frequency response, or its impulse response. And the third question is, do we need an anti-aliasing filter or not? So these are all the questions that you have to address if you are interested in implementing a continuous time filter using a DSP system. Okay. So an example of that is, say my input signal GT is voice being input to a voice recorder. And what you want is, you want to low pass filter that voice. So low pass filter the voice to, let's say, 4 kilohertz. So in continuous time, we understand that operation. In continuous time, you have g of t. You are interested in having h of j omega. To get back g tilde of t, where h of j omega, the goal of that filter is to low pass filter it. So you are interested in letting all frequencies pass below 4 kilohertz, so 8000 pi, and you want to cut off all the other frequencies. So this is your desired action, but how do you achieve that action using a DSP system? Now, to answer these kinds of problems, we'll first ignore the anti-aliasing filter. So our first derivation, which will relate the continuous time systems to DSP systems, will say that ignore anti-aliasing filter for the time being. This is because we know when we need the anti-aliasing filter. It is when we cannot guarantee that our input signal is fully band limited. So let's, for the time being, ignore that part. So I have input signal g of t. I pass it through a continuous to discrete converter with time period t. Then I pass it through a discrete time system with frequency response h of e to the j omega. And then I convert it back to a continuous time signal. And my goal is to understand what is the equivalent frequency response in continuous time of these three blocks together. Now, to understand that, what we will do is go from one block to the other and keep on accumulating our knowledge. Okay? So let's call that this is Gn and this is Yn. Okay? So in the previous lecture, we understood what is the relationship of Gt to Gn. We understand this relationship. So we can mathematically we have, and we will derive all of these things in the frequency domain, because that is what will help us relate the DSP system to the continuous time system. So let's look at the first step. What is the what are the frequencies in Gn? They are given by g of e to the j omega, and if this continuous time signal has frequencies g of j omega. So how are the two related to each other? So the relationship of the continuous time to discrete time is given by three operations. The first is you have scaling of the frequency axis. So I'll write the frequency axis gets scaled by multiple of t. Okay, so little omega equals capital omega equals little omega over t. The second thing is you have scaling of the amplitude by 1 over t. And the third thing is you have multiple shifted copies which are shifted by multiples of 2 pi. Okay. So this is the formula that you get. Now, we also understand from the last topic's discussion what is the relationship between the frequencies of my output G tilde of j omega and the frequencies of this discrete sequence Yn. So let's call the Fourier transform of Yn as y of e to the j omega. Just did it in the last lecture. Assume right now, we'll just assume that there is some reconstruction filter. So reconstruction filter is given by hr j omega. So the output frequencies, and let me actually call this 3 because this is the third block. But we are doing it because we already know the answer to this part. G tilde of j omega, this is related to, the first thing is that you have a scaling of the frequency axis, but now the other way. Your scaling of the frequency axis is by division by t. So your original frequencies are e to the j, y e to the j, but instead of little omega, you get capital omega t. Right? Which means that you are dividing your frequency axis by capital T. Right? Your capital omega is little omega over your little omega is capital omega t, or your capital omega is little omega over t. And then you multiply that with your reconstruction filter. So what is the missing link now? We need to understand what is the relationship of this block, the input and output of this block. So let's call this 1, this is 3, and this is 2. 1 and 3 we know from our last topic. What about the input-output relationship of block 2? So let's call the Fourier transform of Gn as g of e to the j omega. So the output of block 2, y of e to the j omega, that is equal to, so block 3 is simply your output frequencies are multiple of your input frequencies, g of e to the j omega, times your frequency response, which is h of e to the j omega. Okay. Now, why are we writing all these blocks? I just want to remind you, because what we are trying to do is we are trying to write that the final output g tilde j omega is equal to my input g of j omega times some frequency response h effective j omega, and then we'll call this our effective LTI system. That's what we are trying to do. So to do that, what we'll do is we'll just start inputting different values in these expressions. So let's start with 3, because we want to write g tilde j omega equal to something. So start with 3. So we have g tilde j omega equals to hr j omega y of e to the j capital omega t. Now, from block 2, we know what is y of e to the j omega. So I'll just replace this with my answer in 2. So I get hr j omega times, now everywhere I have little omega, I just replace that by capital omega t. H of e to the j capital omega t, g of e to the j capital omega t. We still don't have this expression. We want our output frequencies to be some multiple of our input frequencies. So I still don't see my input frequencies in this expression. So what do I do here? I look at block 1. This is g e to the j omega, little omega with little omega replaced by capital omega t. So I just replace this with 1. So I get h r j omega, h of e to the e to the j omega t, and now I have 1 over t summation k from minus infinity to infinity, g of j, I replace little omega by capital omega t, divided by t, I get capital omega minus 2 pi over t times k. So this formulation g tilde of j omega, this is always true. Now we see the output frequencies as some function of input frequencies, but we still don't have this form. So now we specialize to the case of an ideal reconstruction filter. So just want to remind you, this expression is always true. Now assume an ideal reconstruction filter. So an ideal reconstruction filter is HR j omega is T for omega less than or equal to pi by T and 0 otherwise. Right? So in the case of an ideal reconstruction filter, if I write this expression, G tilde of j omega, I'm working with this, let's call this star. So back to star, it is h of e to the j omega t times hr of j omega times 1 over t summation k from minus infinity to infinity g of j capital omega minus k omega t. So 2 pi over t is just k omega t. Now this is, if you remember, this is nothing but this is my reconstruction formula. This is what we obtain when we are going from discrete time to continuous time. And if I have an ideal reconstruction filter, then what happens is that you only look at so this summation from here to here. This summation is going from minus infinity to infinity because you are looking at multiple copies. But because of the ideal reconstruction filter, you only want to focus on minus pi by t to pi by t. Okay? And if we assume now at this stage, let's make another assumption that g of j omega was band limited to pi by t, so there was no aliasing. Okay, there was no aliasing, and if that is the case, then this whole expression in this rectangle becomes nothing but g of j omega. Okay. Because you have no aliasing, so you have no overlap from minus pi by t to pi by t, and then the reconstruction filter simply throws away all the remaining copies beyond minus pi by t to pi by t and keeps only the copy that is inside it, which is your true frequencies. So under the assumption that your input signal was band limited to pi by t, you had no aliasing, or you satisfied the Nyquist criterion, what we end up getting is that g tilde of j omega equals to h of e to the j capital omega t times g of j omega. Okay. And this is in the form that we wanted. We wanted our output signal frequencies. So we wanted our output signal frequencies, these ones, in the form of, so our output signal frequencies should be in the form of input signal frequencies times some function of capital omega. And that is what we have ended up getting. We have our output frequencies equal to our input frequencies times some function of capital omega. So we call this our effective continuous time system. This is our effective continuous time system. Now, what is this saying? What this is saying is that if I again, just going back to that block diagram, if I start with an input signal, I pass it through a continuous to discrete converter with time period t, then I filter it with some discrete time system, and then I do reconstruction with the same time period t to get g tilde of t. The effective action of this is equivalent to my discrete time filter h of e to the j omega, h of e to the j little omega, with little omega replaced by capital omega t. So my h effective, this acts as an effective filter, h effective of j omega, that is equal to h of e to the j little omega with little omega replaced by capital omega t. Now this is true as long as two things happen. There are two conditions we gave. One condition is that we have ideal reconstruction filter, and the second condition is that Nyquist criterion is satisfied. So let's take the example where your h of e to the j omega was a low pass filter, a discrete time low pass filter. So it was, let's say, 1 for little omega less than or equal to pi by 4, and 0 for pi by 4 and pi, and of course it repeats itself after that. So if in this block diagram I had this low pass filter and we had ideal reconstruction filter and Nyquist criterion, then effectively in the continuous time we will have effectively a filter, continuous time filter, whose frequency response will be given by h of e to the, whose frequency response will be h effective of j omega equals to, so what is the only effect that we are having? Little omega gets replaced by capital omega t. So this is 1. So little omega gets replaced by capital omega t. So it's capital omega t is less than or equal to pi by 4. Okay. And we are only looking at, so one thing I forgot to mention is this is h of e to the j omega for omega less than or equal to pi. So you only focus on the main from minus pi to pi region. Okay. So I have 1 for capital omega t less than or equal to pi by 4 and 0 otherwise. And if I want to then write it as purely a function of omega, then that will be 1 absolute value of omega less than or equal to pi by 4 over t. I take the t to the other side and 0 otherwise. Okay. So if I have a low pass filter in the discrete domain, what is the effective action of this in the continuous domain? What kind of a filter is this? What kind of a filter is this? So the effective action of a discrete time low pass filter is a continuous time low pass filter But what is the difference? The discrete time low pass filter had a cutoff of omega c equal to pi by 4, whereas the effective continuous time filter has a cutoff of capital omega c equal to pi by 4t, which is equal to little omega c over capital T. So effectively, if you implement a discrete time filter, what you end up getting is a continuous time filter. Again, under the assumption that we have talked about, you end up getting a continuous time filter, but the axis of the continuous time filter is a scaling of your discrete time filter by a factor of 1 over t. So if you start with a low pass filter, you end up with a low pass filter, but your cutoff, instead of the previous cutoff, it becomes the previous cutoff divided by t. Okay, so just to recap, the equivalent continuous time LTI system and the implemented discrete time LTI system are simply related to each other by a scaling of the frequency axis. Now there can be two ways of encountering this problem. So one way is that under the two conditions of your input signal is band limited and you satisfy the Nyquist criterion and the reconstruction filter is ideal. One thing is that we are given the discrete time system and we need to know what is its effects or what is the equivalent continuous time system. And when we say what is the equivalent continuous time LTI system, we can simply ask about either its frequency domain interpretation or its time domain. So we just focus on in frequency domain, the equivalent system is given by a scaling. So what you do is, again, it's very easy to remember which way the scaling goes. The frequencies of discrete time systems are radians. The frequencies of continuous time systems are radians per second. So you want to go from radians to radians per second, the frequency axis must be scaled by 1 over t. So that you divide the radians by t so that you get radians per second. So it's e to the j capital omega t for capital omega less than or equal to pi by t and 0 otherwise. Okay. Now here is the other factor that, of course, discrete time system is periodic, so it keeps on going. You only go from pi by t, minus pi by t to pi by t in the continuous time domain. Or another way you can think of it is, this is the equivalent is, I'm saying you have h of e to the j little omega and then replace little omega by capital omega t, which means capital omega is little omega over t. So that is one case. And the second case is that someone gives you a continuous time problem specification. So we are interested in a desired continuous time LTI system. So someone says we are interested in a frequency response that is age effective j omega. The problem in that case is what should we have as the discrete time LTI system? And again, that simply means what is h of e to the j omega. So someone tells you, I want to implement a low pass filter with a cutoff of 2 kilohertz. The question is, what is the equivalent discrete time system? Okay, and in that case, the relationship again is simply a scaling of frequency axis, but now the other way. So your frequency axis in continuous time, you are given its radians per second. Now you want to obtain radians. The scaling should be your axis gets multiplied by t, multiplied by second, so that you get back radians. So h of e to the j omega is h effective j capital omega, but with capital omega replaced by little omega over t. Or that is equal to h effective j little omega over t. Now the caveat is that this little, you only go up to pi. And after that, you know that since it's a discrete time system, there is periodic repetition. And one of the key things to remember in going between the continuous and discrete time systems is there is no scaling of the amplitude. That's an important point to remember. The amplitudes in going from continuous to discrete time for the systems, not for the signals. Here we are talking about equivalent systems. The amplitudes for the systems don't change. So in general, the effects of scaling, of course, will depend upon the shape of the filter that you are talking about. But for ideal, in the case of ideal filters, what happens is that a low pass filter in discrete time acts as a low pass filter in continuous time. Because all that happens is there is either there's just sort of stretching or compressing of the frequency axis. That's it. Again, under the two conditions that we talked about earlier. Similarly, a high pass filter stays a high pass filter. A band pass filter stays a band pass filter. A band stop filter stays a band stop filter. The main challenges are what are the cutoffs of those filters. So that is simply given by this scaling relationship. So if I have a discrete time versus a continuous time, we know that a low pass filter is simply given by what is its cutoff. So for low pass filter, in discrete time you say, what is the cutoff frequency? Maybe pi by 4. Well, in continuous time, you will still have a low pass filter, but its cutoff will become capital omega c equal. So capital omega c in that case will be little omega c over t. Simply a scaling of the frequency axis. A high pass filter, again, it's described by a cutoff. So if it's omega c, In continuous time, it will again be little omega c over t. A band pass filter is described by 2 points omega c1 and omega c2. So omega c1 tells where the band starts and omega c2 tells where the band ends. Well, in continuous time, it will still be a band pass filter, and the band will start at capital omega c1 equal to little omega c1 over t, and it will end at omega c2 equal to little omega c2 over t. And of course, you can reverse all of that. You could start with continuous time and then do multiplication with t. Band stop filter. Again, it's given by 2 parameters. Where does the stop band starting point is and where does the stop band end? So it's again given by omega c1 and omega c2. And the relationship in continuous time is exactly the same. The start and end frequencies are given by a scaling of the axis, omega c2 equal to little omega c2 over t. Now, sometimes you are interested in getting, so this is the relationship in the frequency domain. What is the relationship in time domain? So you have a discrete time system, h of e to the j omega, and of course it has an impulse response given by h of n. And you have a equivalent continuous time system, h effective j omega, and it has a continuous time impulse response h effective t. We understand the relationship between the frequency domains, right, which is the relationship that in most cases we work with that relationship, at least for translation of our filters. But it is still important to know the relationship in time domain also. We won't go into the proof of that, but the relationship is actually that the discrete time impulse response is simply equal to samples of your continuous time impulse response. So you take your continuous time impulse response and you take samples of that every t seconds, and you also multiply it with capital T. So this is what you get. So just using this relationship, for example, we know that a continuous time LTI system that is an ideal low pass filter, its impulse response is sync. So what will be the impulse response of a discrete time LTI system that is a low pass filter? Well, you are going to take samples of that sync and you will get back a sync. Okay. So this is the relationship in time domain. Okay, all this discussion was predicated on the notion that your input signal is band limited. So let's talk about the case when g of t, the input signal, is not band limited. So if g of t is not band limited, there are two things we could say. We could say, well, one is that I can't process that signal in a DSP system. That's not a very useful answer. So the other aspect could be, if it's not band limited, then so we simply pass this G of t to an anti-aliasing filter with frequency response h of AAJ omega. So this is an anti-aliasing filter. And once we pass it through an anti-aliasing filter, we get this new signal. Of course, that is not the same signal as our original signal. Now that is band limited. We then pass it through continuous to discrete. We have the same rest of the block. We pass it through discrete to continuous. And then we get YR of t. The question is, what is the equivalent relationship between the input of this entire system and the output? Well, to understand that, we have to understand that we are just looking at cascade of two LTI systems. So we just argued that if the input to this dashed block is band limited and we satisfy the Nyquist criterion, that this entire dashed block acts like a continuous time LTI system. So I could replace my above block by actually two LTI systems. Okay. And if I am now interested in finding the input-output relation in frequency domain, I know that the output YR j omega, that is equal to the input of this block in the frequency domain. So that is GAA j omega times the filter H effective j omega. And further, I know that this GAA j omega, that is the output of this LTI system. So that is given by my input frequency. So that is G of j omega times the frequency response of my anti-aliasing filter HAA of j omega. So I plug that in this equation and I get that YR j omega equals HAA j omega times H effective j omega times G of j omega. So what happens is that if you use an anti-aliasing filter and then the rest of the DSP system, the entire system acts as a continuous time LTI system, but now the frequency response of the continuous time LTI system is given by multiplication of your anti-aliasing filter's frequency response with the effective frequency response of the rest of the block. And you can replace that. So that is HAA j omega times H of e to the j capital omega t, right, where H of e to the j omega is given here. So the same thing that we learned earlier, if you have an anti-aliasing filter, the only thing that happens is that your effective frequency response gets multiplied with the anti-aliasing filter's frequency response. Okay. So this concludes our discussion of how can DSP systems be used to mimic continuous time processing of continuous time signals. And in that entire specification or analysis of DSP systems, here are some of the DSP design questions that you have to address. The first question is the input to the system band limited or not? So that can also be asked in terms of, do we need an anti-aliasing filter? And you are fully equipped to answer that question depending upon your application. The other question you have to address is, what should be the sampling time or frequency? Again, we know that the answer to that depends upon the bandwidth of my input signal, or whatever is the anti-aliasing filter that I'm using that restricts the bandwidth. Okay. Now, the third question is, what should be the filter in discrete time? So what should be the discrete time filter? And the answer can be given in terms of Hn or h of e to the j omega. And again, the discussion today helps us address that answer. If we are given, for example, if we are interested in doing low-pass filtering of our signal, then we know that our discrete time filter must be a low-pass filter also. All we have to do is an appropriate scaling of the cutoff frequency. Okay. So we have addressed all these 3 points. The fourth point is how to design or implement HN. That problem is called the filter design, and that we'll come back to it later.